Hey, this is AP Chemistry lesson for Thursday evening, September the 12th, due the next day. And this is a lesson on atomic mass and molar mass and what a mole is. It's a very important concept in chemistry. And what it essentially is it's a large number of atoms or molecules that's large enough for us to actually see and weigh on a scale, because we can't weigh or see individual atoms or molecules. So somebody came up with the idea, let's have a big basket, a big bundle, a standard number of molecules. It's very, very large, that's big enough for us to be able to see and to actually work with. And this was developed by a man named Amedeo Avogadro, and he came up with a interesting number called Avogadro's number. And the number is this, so we'll answer the first question. It's 6.022 times 10 to the 23rd. And what is a mole? It's exactly the same thing. So when we actually work with this number in chemistry calculations, we don't call it Avogadro's number, we call it a mole. Just a short way of referring to this number. A mole is just a number, just like a dozen is a number. You all know what a dozen is. It's 12. But usually people think of a dozen eggs, but it could be a dozen anything. You could have a dozen cars, a dozen people. It's just simply a word that refers to a specific number, 12. So a mole is a word that refers to a specific number of 6.022 times 10 to the 23rd. Why this number? Well, that's going to be one of the things we answer in this lesson today. Why did they pick this number? Why not some nice round number like 1 times 10 to the 20th? That would be a 1 with 20 zeros behind it. That's a big number. Why couldn't they have chosen that? Well, we're going to find that out. Okay, so atomic mass, as we know, is the mass. Okay, atomic mass is the mass of an individual atom or molecule. In this case, we're going to just say atom, but if you put them together and have a molecule, it can be, you could refer to that as the atomic mass or molecular mass. Okay, mass number is when you round the atomic number. Round the atomic mass. That was my mistake. Round the atomic mass to a whole number. And we remember what we use that for. That would tell us the number of protons and neutrons in the nucleus. It's a whole number of protons and neutrons. There's never a fraction of a proton or a neutron. So it's when you round the atomic mass to a whole number. And we used that when we were constructing the atom. What is molar mass? Okay. Well, atomic mass is the mass of an atom. Molar mass is the mass of a mole of atoms or molecules or whatever it is you're talking about. So it's the mass of 6.022 times 10 to the 23rd of whatever the particle is you're talking about. Finally, what is stoichiometry? Stoichiometry is kind of a funny word. It's the math related to chemistry. And more specifically, to chemical equations. And chemical equations are the heart and soul of chemistry. And we're going to get into those within the next week. So those are the basic definitions you should know for this assignment. All right, so what we're going to do is figure out what the atomic mass is of various molecules. We know the atomic mass of individual atoms, and the way that you come up with the atomic mass of individual molecules, or it could be formula units if it's an ionic bond, is you simply add the mass of all the atoms in it, and you come up with a total. So if we take, for example, this is water right here, so I'm going to write H2O right there. So if we take the element hydrogen, we have 2 atoms of hydrogen. And I rounded this once upon a time, but I don't want you to do that. So I'm doing this to show you the change I want you to make on your sheet. So the mass of hydrogen is not 1, it's 1.01. If you look at your periodic table. So we'll go to 2 places after the decimal, which is what your periodic table does. You should have a periodic table in front of you, preferably the one you got in class, but you don't have to use that one. So if you multiply that by 2, you end up with 2.02 AMU, atomic mass units. Remember, the atomic mass unit is the mass of a single proton or a single neutron. Okay. Now oxygen, there's one atom. It's 16. To be proper, we should call it 16.00 times 1, and that's going to give us 16.00 atomic mass units in a water molecule for the oxygen. And the final is we simply add up how much the total mass is that we have. So 2.02 plus 16 is going to give us 18.02 atomic mass units is the mass of one water molecule. So that's how you do it. It's a very simple process. Okay, so I'm giving you several to do, and these are the ones up above. We've already done water. So do the rest. Acetic acid is vinegar. Carbon dioxide is what you exhale. There you see vitamin C is a vitamin you're familiar with, and aspirin. You notice how they both have carbons, hydrogens, and oxygens in them. Methane is natural gas. That's the kind of gas that comes out of our gas fixtures back here in the room. And then you got glucose. We did that one as an example in class. Ferrous oxide, that's the one compound on here that's an ionic bond. It has iron, a metal, and oxygen, a nonmetal, but you can still do the same process with this. Sulfuric acid, we're going to be doing a lot of work with acids and bases. And cinnamon, okay? So if you wonder what a cinnamon molecule looks like, there it is right there, okay? All right, so here we go. We're going to do this kind of quickly. You can always pause it if you need to. And let's go. So we're going to start with CH4. We don't necessarily need all the rows here. I put 4 in most of them, though. Okay, so you have carbon and hydrogen. The number of atoms of carbon, you have 1. I'm looking at the subscript here. If there's no subscript, it means there's 1 carbon atom. Okay, the atomic mass of carbon is 12.01 times the number of atoms, which is 1. And that gives us a total mass for the carbon that's in methane, in a methane molecule, as 12.01. We should always put our units of measure. Don't just leave that blank. So it's AMUs, okay? All right. Next is hydrogen. We have 4 of those. So it's 1.01 times 4. That's going to give you 4.04 atomic mass units. And so now to get the mass of a methane molecule, you just simply add the 2, and you get 16.05 AMU, and that is the atomic mass of a single methane molecule. All right, and we don't need this line down here. Okay, next up, let's do glucose. Now that's got a little bit bigger numbers in it. So it's CHO. There's 6 atoms, there's 12, and there's 6. The atomic mass. One of the reasons I have you do this repetitively is I want you to kind of memorize these atomic masses. It's not required, but it's nice if you know them, and you can work a lot more quickly in the future in future chemistry problems. So the atomic mass is 12.01 times 6. Okay, and you multiply that out, you're going to get 72.06 mass. Again, I want to put units always up here. Okay, next is hydrogen is 12. Well, it's 1.01 is the mass, times 12, the number of atoms. And that's going to give us 12.12. That's the atomic mass for the 12 hydrogens. And finally, we've got oxygen, which is 16.00 times 6 oxygen atoms. You multiply that, you get 96.00. And if you add all those up, you end up with 180.18 atomic mass units is the mass or the weight. We can use those words interchangeably in chemistry for a glucose atom. Next up, ferrous oxide. Okay, so we got Fe and O. And we have 2 iron atoms. Okay, so there's 2 of these. Each iron atom is 55.85. Times 2. All right, and for oxygen, we have 3 of those. And each one of those, 16.00 times 3. Okay, so let's do this one first. It's easiest. It's 48. Okay, and then we've got to multiply the 55.85 by 2. Okay, and when we do that multiplication, we have 111.7. I'm not going to worry too much about significant figures here at this point, although that would be 4 significant figures. Let me make a point. If you're multiplying by a whole number of something, point we didn't make before, this does not limit the number of significant figures. This is exactly 2. You want to multiply it by exactly 2. So that's 2.00000 forever. That's an infinite number of significant figures. Okay, so don't feel that that limits your significant figures. Okay, but this one does. This one does. This is a measured value. Okay, so now we're ready to add the two together. So it's 111.7 plus 48, and that's going to give us 159.7. I think I did that one right. Okay, and that's the atomic mass units. That's the mass of iron oxide. Okay, next up is sulfuric acid. Okay, and now we have to add those three numbers together. And let's see if I can keep this from slipping down here. Okay, right there. Okay, so you add those three. And we get 98.09. Always check my math on these because I'm doing the math as I do the sheet. Okay, there you go. There's H2SO4, sulfuric acid. All right, next up. Okay, and so now I did skip a page, so I'm going to backtrack now. So we're going to do acetic acid now, so you can just go back to the previous page. And it's C2H4O2, so let's go ahead and do that. Okay, carbon we have 2, hydrogen we have 4, oxygen we have 2, 12.01 times 2, 1.01 times 4, and 16.00 times 2. And so this gives you 32.00, 4.04, and 24.02. You add that up and you get 32, 42, 52, 56, 60.06. Atomic mass units for acetic acid. Okay, carbon dioxide, a little bit simpler one. C and O and CO2. 1 carbon, 2 oxygens, oops, I'm sorry, 16.00 times 2, and that's going to give us over there 32. And now it should just add, and you have 44.1. That's one we'll be using a lot in this class. Okay, so 44.01 atomic mass units for carbon dioxide. Okay, next is vitamin C, another carbon, hydrogen, oxygen compound. Okay, carbon, we have 6, hydrogen 8, oxygen 6. Okay, so 12.01 times 6. You have 1.01 times 8. And you have 16.0 times 6. This is going to give you 72.06. This will give you 8.08. And this will give you 96.00. So that's going to be 168, 176, 177.4. Check my math on that. Do it yourself. 0.04 rather. And now, whoops, I'm sorry, that was 0.14. Okay, so I hope you checked my math on that. 177.14 atomic mass units. Okay, aspirin. It's amazing how many different things, how vitamin C, aspirin, acetic acid, all these things are CH&O, carbon, hydrogen, and oxygen, even though they're completely different substances. Okay, so here we got CHO again. Okay, and in carbon you have 9, hydrogen you have 8, and oxygen you have 4. Carbon's going to be 12.01. Hydrogen is 1.01. Again, the repetition gets you to where you memorize these atomic masses. You'll be using, particularly for these, you see how often we're using these, and you'll be using them quite a bit in this class. So it's good, while you're not required to memorize them, it's good to have them committed to memory. Okay, so now we're going to add these up. So we got 64.00, and I'm sorry, that should be an 8 there. And that's going to be 8.08. And then we have 12 times 9, that's 108, 108.9, 0.09. Okay, and so now we just add them up. I'm not going to try to do this with my head. Okay, 180.17. And atomic mass units, always unit of measurement at the end. Okay, move on to the next page. Okay, and we'll end up with one that's kind of fun. This is cinnamon. Again, it's got C's and H's and O's. It also has nitrogen in it too, see, okay? So C, H, N, O. So carbon we have 11. Hydrogen we have 13. Nitrogen 1, and oxygen 1. Okay, so we're going to do carbon 12.01 times 11. Hydrogen 1.01 times 13. And then nitrogen is 14.01. times 1, and oxygen 16. And we got the carbon up there. It's going to give us 132.11. And this is going to be 13.13. Okay, there you go. So now we're adding all these up. Okay, and I get 175.25. Okay, so it should always be, anytime you do one of these assignments like this, always be attempting the problem yourself before you watch me do it, okay? And there we go, and we should write this down here. And there's cinnamon. Okay. Now we're going to move on to a different concept. we're going to move on to the concept of the mole, which we defined at the beginning of this assignment. And a mole is this many particles. It could be a mole of atoms, a mole of molecules, a mole of pizzas, a mole of dollar bills, a mole of cars, you name it. It's just a number, just like a dozen. But it's a very special number. It's a very specific number. We asked the question earlier, why didn't they just call a mole 1 times 10 to the 20th? That's a big number. They could work with that number. They could have picked any number they wanted for a mole, but they chose this one. Why? Well, let's look at this sample problem, and you're going to see why. Okay, so what we just did was this over here. We just computed atomic masses and the masses of the molecules. So here, if we have CO2, carbon dioxide, we have 1 atom of carbon, 2 atoms of oxygen. That gives us 1 molecule of CO2. Be clear on that concept. A motorcycle is 2 wheels and 1 motor for 1 motorcycle. So it doesn't give you 1 plus 2 or 3 motorcycles. It gives you 1 motorcycle with those 3 parts. These are each parts of this whole. Okay, and then I did do some rounding here, but normally I want you to do it with decimal places. So I just rounded carbon 12.01 to 12. There's 1 of those, so you get 12 AMU, 2 times the oxygen, 32. So you end up with 44 AMU rounded for carbon dioxide. Okay, so what is a mole? Well, a mole is any number you want it to be. So if we say we have 1 atom of carbon and we want 1 mole of carbon, we could have called a mole whatever we want, as I just said. We just say whatever number a mole is, we're going to make a translation from 1 atom to 1 mole of carbon. But here's the magic of this number right here. If we know the mass of carbon in AMU, that it's 12, okay, then if we take exactly this number of carbon atoms, this is the only number that will make this a true statement, we will get exactly the same numeric value for our molar mass. In other words, we take 1 carbon atom, we multiply it by a mole of carbon atoms, or by a mole, we end up with a mole of carbon atoms that's going to have a molar mass of exactly the same number as this, 12 and 12. If this number were anything other than 6.022 times 10 to the 23rd, we multiply 12 by any other number, it won't give us 12 there. So what this does is it relates our microscopic mass, which is measured in AMUs, which we can't measure on a scale, they're too small, to our molar mass, which is in the standard unit of measure for mass in chemistry, which is a gram. It converts it to the same exact numeric value of grams, 12 to 12, and we can measure in grams. We did it already in this class when we were on the scale. So that's the magic of this number called a mole. So it's the same thing with oxygen. We have 2 atoms of oxygen. 2 atoms of oxygen. If we multiply it by a mole, we have 2 moles of oxygen. Okay, but we know that the atomic mass of oxygen is 32. If we multiply 32 AMUs by this number, we end up with exactly the same number, but in grams. So 32, 32. And that relationship between mass in AMUs and mass in grams is really important, and that's why this number, being exactly what it is important. So anyway, we end up with a molar mass of 12 grams for carbon. For the 2 oxygens, it's 32. So we end up with a molar mass for carbon dioxide of 44 grams. Again, exactly the same numbers for a carbon molecule, except the carbon molecule is 44 AMU, and the mole of carbon is 44 grams. So we call this a molar mass. It's the mass of a mole. As a final question, I just asked you, how many atoms or molecules is that? Well, if we have 1 mole of carbon and you multiply that by this number up here, you end up with that number, 6.022 times 10 to the 23rd. Yet I did some rounding here. Okay, what about oxygen? You have 2 moles of that. So that you don't have to actually do the arithmetic down here. It's 2 times 6 times 10 to the 23rd. I just want you to get a concept of what we're talking about in terms of the actual number of atoms or molecules. And since carbon, we have 1 mole of carbon dioxide, 1 mole of carbon dioxide. That's going to be 1 times 6 times 10 to the 23rd, and that gives us that many molecules of carbon dioxide. Okay, so now we're going to do a number of these Now we're going to do a number of these for you to do. So, and then we're going to answer a number of questions for them, okay? So, K2O, that's potassium oxide. So we're going to put a K here, an O here, and a K2O. I said KO2, it's K2O. Okay, number of atoms is 1, number here, excuse me, it is K2O. And then number of oxygens is 1. Okay, so the atomic mass for potassium is 39.10. And of course for oxygen is 16. You're going to multiply that, let's see, that's the atomic mass rounded. Okay, and I'm sorry, here I'm actually also multiplying it by 2, so times 2. So what I'm going to end up with there, and I end up with there, I have 78.2. So the atomic mass is 78.2 plus 16, which is 94.2. That 94.2, actually 20. Okay, so that takes care of, and this is actually an ionic bond, so this is a formula unit. Again, if you don't understand that concept, don't worry about it. We'll get to that. We'll talk about that more later. So it's 94.20 AMU for each formula unit. You can think of it like a molecule, basically. Okay, formula unit. Now, number of moles. Well, I want to have. If I have 2 molecules, I want to have 2 moles. So now we're talking in terms of, remember we used the term in class, this is microscopic, this is micro, this is on the molecular atomic level, and this over here is macro. It's big world. It's stuff that we can see and feel and weigh and touch. So now we're moving into the macro world. We're just doing a translation. So 2 atoms to 2 moles, because I'm multiplying by 6.022 times 10 to the 23rd. So I end up with from 2 atoms to 2 moles, from 1 atom to 1 mole. Okay, and we're not going to add those up. And then the molar mass. And again, this is the beauty. It goes from 78.2 AMU to 78.2 grams. This one from 16.00 AMU to 16.00 grams, something we can actually weigh on a scale, and we get the same numeric value, 94.20 grams. Okay, how many moles do I have? Well, potassium, I have 2 moles, so I have 2 times 6.022 times 10 to the 23rd. And for oxygen, I have 1 mole, so it's 1 times 6.022 times 10 to the 23rd atoms of oxygen. And the K2 and the O gave us one again, it's formula unit. We'll call it a molecule just for the heck of it. And this is going to be 1 mole. So 2 moles of this, 1 mole of this give you 1 mole here. And so it's going to be 1 times 6.022 times 10 to the 23rd moles of K2O. Okay? All right. Okay, so now I'm asking you to answer some questions down here. And okay, so I'm going to ask you to answer some questions about this table you just made. There's a few errors in it, but we can just correct those quickly as we go along. So it's not, question 1, how many, shouldn't be water molecules, it's just how many molecules in 1 mole of K2O. So you come over here and you look at, this is the number of molecules in K2O, and in 1 mole, there's this many. So notice that everything is referenced around 1 mole. So we're going to answer all of our questions based on 1 mole. So 1 mole of K2O is going to have 16 grams of oxygen. It's going to have 1 mole of oxygen. It's going to have 78.2 grams of potassium. It's going to have 2 moles of potassium. It's going to have 2 times 6.022 times 10 to the 23rd atoms in it. So that's that. So if I ask you for some number other than that, you simply do a multiplication or a division. So let's see how that works. So 1 mole, how many molecules in 1 mole? Very simple. It's 6.022 times 10 to the 23rd. Okay, next question. How many grams is 1 mole of K2O? So there's 1 mole, and this is how many grams it is. So the answer is 94.20 grams. Okay. I generally would like you to write these out as complete sentence answers, but I'll let that go for now, okay, since you have the question right there. Okay, let's keep going on this. Okay, so we moved on to the next page. Again, I have to make a couple of corrections here, but we'll go ahead and do those and work with that. Okay, so the next question is, how many moles of oxygen in 1 mole of K2O? So here's 1 mole of K2O, and there's 1 mole of oxygen. So the answer is 1 mole. Here's what I would like you to get in the habit of writing. 1 mole, and then in parentheses, what the substance is, what the element is, the compound, whatever. You got to get used to unit of measure plus the compound or element. Okay, next thing is, trying to keep this on the screen here. So, how many grams of oxygen in 1 mole of K2O? So again, you come up here, this is 1 mole, and there it is. It takes 16 grams of oxygen to produce 1 mole of K2O. So 16.00 grams per mole. Okay? All right, next up. How many carbon atoms in 1 mole? So we look here, this is 1 mole, and we come up here, okay, I'm sorry, and that's an error. Let me correct that. So it should be how many potassium. How many potassium atoms in 1 mole of K2O? All right, so here we have 1 mole of K2O. This is always our reference. Okay, so that means we have 2 moles of potassium, and the number of atoms is 2 times Avogadro's number. So the answer is 2. You don't have to do the math on it. Just show that you understand the concept by writing it like this. 2 times 6.022 times 10 to the 23rd. Okay, atoms of K, of potassium. Okay, and one more small correction. Change carbon there again to potassium, K. So how many grams of potassium in 1 mole of K2O? So here's 1 mole, and here's potassium. It takes 78.2 grams of potassium to make 1 mole of K2O. So 78.2 grams, unit of measure, and element potassium, grams of K. All right, and that takes care of that particular compound. Let's go ahead and do water. This is the last one I'm going to do on this video. I don't want you to have to be there. What I want you to do is do the rest on your own, and we're going to talk about them in class. Okay, so here we have water. So let's go ahead and write down what we have. We have H and O and H2O. We have number of atoms of hydrogen. We have 2 and 1 of oxygen. Atomic mass is 1.01 times 2, and that's going to be 2.02. This is in atomic mass units. So we're on the microscopic level now. And for water, it's 16.00 times 1. Okay, and that equals 16.00 atomic mass units. Okay. If we add those together, the atomic mass of the water molecule is 16 plus 2.02. That's going to give us 18.02 AMU. Okay? All right. So now we're going to translate everything into moles. And by the way, how many molecules of water does that make? These two are in atoms because they're each individual atoms, but this is a molecule. So how many do you have? Again, a motorcycle has 2 wheels and 1 motor gives you 1 motorcycle. So there's 1 molecule of water. Okay. All right, now moles. We're going to multiply by, I'll just put it right here, times 6.022 times 10 to the 23rd. that standard batch of atoms or molecules, and that's going to give us this number. We just decided that's a mole, so 2 times 1 mole is 2 moles. So it's 2 moles. That's asking how many moles. 1 times a mole is 1 mole. 1 times a mole is 1 mole. These numbers stay the same. That would be true if any number was defined as a mole. But this is where the magic of this number comes in. How many grams? And we should always write that here in grams, molar mass in grams. It's 2.02 AMU, so it's 2.02 grams. Okay? 16.00 AMU, so it's 16.00 grams. And finally, 18.02 AMU, so it's 18.02 grams. Okay, and now how many atoms or molecules is that? Well, it's 2 moles, so that means it's 2 times 6.022 times 10 to the 23rd. This one is 1 mole, so 1 times 6.022 times 10 to the 23rd. And finally, it's 1 mole of water, so it's 1 times 6.022 times 10 to the 23rd. And that fills out our table. Now we're going to answer our questions down here. Again, remember that we just built 1 mole of water. So all of these numbers that you see over here relate to this number here, 1 mole of water. Okay, so how many water molecules in 5 moles of H2O? So if 1 mole has 6.022, then it's 5 times 6.022 times 10 to the 23rd. And if you do the math on that, it comes out to what it is. I don't care if you do the math. That's not really that important. I want to be sure you understand the concept. Next, how many grams is 2 moles of H2O? Well, 1 mole of H2O is 18.02, so 2 grams, and yeah, you can go ahead and multiply this one out, is 2 times 18.02 grams, and that's going to equal 36.04 grams in 2 moles, okay? And that's of H2O for 2 moles. Okay, so see, it's just a matter of relating to 1 mole these numbers, so if you multiply this, you multiply these. Okay, next, how many moles of oxygen in 8 moles of H2O? Well, in 1 mole of H2O, we have 1 mole of oxygen. So in 8 moles of H2O, we have 8 moles of oxygen, so that's 8 times 6.022 times 10 to the 23rd, and that's going to be moles of oxygen. All right. How many grams of oxygen in 3 moles of H2O? So this is for 1 mole. How many grams of oxygen in 1 mole? There's 16 grams. When I want to make 1 mole, I need 16 grams of oxygen. So if I want to make 3 moles, I multiply this by 3. So it's 3 times 16.00, which gives us 48.00 grams of oxygen. You getting the hang of this? I hope so. Okay, how many hydrogen atoms in 17 moles of water? Okay, so for every 1 mole of water, there's 2 moles of hydrogen. So if I want 17 moles of water, I need 17 times 2. So it's 17 times 2. And to know the number of actual atoms, you have to multiply that by Avogadro's number. Okay, and that's how many atoms of hydrogen. And again, it's not important on this that you do the math. I'd like you actually to leave it like this so you see the concept. If I want 17 moles of water, then I have to multiply this by 17. That means I have to multiply the number of moles of hydrogen by 17 to get 17 moles of water. And then I have to multiply that 17 times 2 is 34 by this number over here. Okay, by 6.022 times 10 to the 23rd. All right. One more. Hydrogen. How many grams of hydrogen in 3 moles of water? So in 1 mole of water, there's 2.02 grams of hydrogen. So in 3 moles, there's 3 times 2.02. So 3 times 2.02. I tell students a lot of times that this is cooking class. You're doing the same thing in this class that you would do in a cooking class. You're scaling things up, you're scaling things down. You want to make 1 cake, you need this much sugar. You want to make 3 cakes, you need 3 times that much sugar. Okay? That's what this really is. And we can give that a number. That's 6.06 grams of hydrogen. Okay, so there we go. We've completed water. I'm going to leave the rest for you, and we're going to talk about it in class tomorrow. Do them on your own. You won't have the solutions. It's one of the few times. I'm not going to necessarily check them all. They're not all check problems, but just go ahead and do them on your own. Let's check them in class tomorrow. Let's talk about this tomorrow, and we'll move on to balancing chemical equations as well. There's a possibility I might not be in class. That's why I'm giving you an assignment rather than a lab. If I'm not in class, I will have a solution sheet for these for you to use. So anyway, have a good day, and we'll see you in class tomorrow, I hope, or on Monday if I'm not there.